Welcome to the boardroom. Listen, if you are sitting for the Cambridge Computer Science exams, specifically syllabus 0478, 0417, 2210, or 9618, you are no longer just a student. You are a strategist. Today we are taking a notoriously tricky topic, data transmission, the sheer mechanics of our digital world, and we are going to use it to hack the examiner's marking scheme. Now, I want to introduce you to two students who represent the biggest traps in these exams. First, we've got Alex. Alex is brilliant, okay? Overloads every answer with raw computer science facts, writes a whole essay, but zero analysis. The examiner gives him half marks because he never actually answers the question. Then we have Sam. Sam rushes, Sam completely misses the command word requirements, and leaves easy marks on the table. Today we're looking at their flawed answers, side by side, covered in red pen, and I'm going to show you exactly how to transform them into top-tier, boardroom-ready responses. Pitch your answer to the board. Justify every point with data and strategy. Let's get into it.
Here is our strategic agenda for today's session. We are covering the 5 pillars of data transmission: the data packet journey, direction and delivery methods, the universal serial bus, catching transmission errors, and finally, securing data with encryption. But remember, we aren't just reciting textbooks here. We are analyzing how Cambridge tests these exact topics.
Section 1. The data packet journey. Let's look at the first major challenge that trips up students like Alex and Sam on the exam paper.
So, Cambridge loves asking why we don't just send massive, gigabyte-sized files across a network all at once. Alex's answer, he writes, files are big, so we use packets. Well, obviously, Alex, but that doesn't get you the marks. The examiner wants the engineering problem and the precise solution. Data files are literally too large to send across networks simultaneously. They would instantly clog the bandwidth. The strategic solution is the data packet. Data is broken down into these manageable chunks before transmission. What you absolutely must mention to secure the mark is packet switching. By breaking data into chunks, routers, acting as nodes, can independently switch and guide each piece to its destination using the most efficient route available at that precise millisecond. You have to use the terminology: nodes, efficient route, packet switching. That is how you command the examiner's respect.
Now, a classic 6-mark question. Describe the structure of a data packet. Sam rushes this and just writes header, data, and trailer. Boom. He just lost 4 marks. You need to break down the anatomy chronologically and explain the why behind each part. First, the packet header. It doesn't just sit there. It contains the IP addresses of both the sender and the receiver, plus a crucial sequence number. Why? So the receiving station can reassemble the data in the right order, even if packets arrive out of sync. Second is the payload, which is the actual data you care about. Third is the packet trailer. You must mention that this contains a cyclic redundancy check, or CRC, for error checking, and a specific marker to identify the end of the packet. If you give the examiner this level of detail, you're guaranteeing yourself maximum marks. Let's analyze a compare and contrast command word question regarding packet switching. Alex will just list random facts, but we are going to structure this logically. The benefits? Extreme efficiency. You don't tie up a single communication line, and if a sorter goes down, packets simply reroute around the failure. It's incredibly resilient. The drawbacks? Because packets take different routes, they can get lost or arrive totally out of order, which demands processing time at the destination to reassemble. Think about it. Why does your live video conference freeze or buffer? It's because real-time streaming suffers when packets take different times to arrive. Connect the theory to reality for the examiner. Now, before we continue to the core strategy reveal, I need you to take action. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Okay, so we've logically chunked our data. But here is the narrative bridge to our next exam hurdle. How do we actually manage the physical flow of this data traffic? This brings us to the strategy reveal.
Section 2. Direction and delivery methods. This is where we introduce our secret weapon, the PEEL framework. Point, evidence, explanation, link.
Cambridge will ask you to define the directional modes of data transmission. Let's look at how top students structure this using PEEL. Simplex. Your point, data is sent in one direction only. Your evidence/explanation, an example is a computer sending data to a printer, as the printer doesn't transmit back. Half duplex. Point, data travels in both directions, but not simultaneously. Explanation, like a walkie-talkie. You press to speak, release to listen. Full duplex. Point,
both directions simultaneously. Explanation: like modern broadband internet. I'm putting 30 seconds on the clock in your mind right now. Look at how clean that is. When you use concrete, relatable examples from the source material, the examiner physically cannot dock you marks. You are leaving no room for doubt.
Let's escalate the difficulty. Contrast serial and parallel transmission. Sam's rushed answer, serial is one wire, parallel is many. Too vague. Let's apply our strategy. Serial transmission sends one single bit at a time down a single wire. It is highly reliable over long distances because there's minimal risk of interference. Parallel transmission, conversely, sends multiple bits down several wires simultaneously. Yes, it is vastly faster, but, and here is your critical explanation point for the Peel framework, over long distances, those parallel bits can arrive out of sync. This is a massive issue known as data skewing. Therefore, you link it back, parallel is strictly for short, fast internal computer connections, while serial is the gold standard for long-distance reliability.
So, knowing that serial is best for external, long-distance reliability, what happens when the industry needs a universal standard to connect all our everyday peripheral devices? Let's move to Act 3, the transformation, where we turn red pen mistakes into green check marks.
Section 3. The Universal Serial Bus, universally known as USB.
I'm going to give you a 60-second visual timer on screen for this rewrite attempt. The question is, evaluate why USB-C has replaced USB-A as the industry standard. Alex initially wrote about how USB-A is annoying to plug in. That's a layman's answer. Here is the transformed boardroom-ready response. USB-A is an older, asymmetric standard with significantly slower data transfer limits. USB-C, however, represents a monumental technical upgrade. It features a 24-pin symmetrical design, meaning there is no incorrect orientation. More importantly, it supports unprecedented data speeds of up to 10 gigabits per second, effortlessly handling 4K video delivery. When you contrast the technical specifications rather than just user convenience, your mark potential jumps from 20% right to 100%.
And here is the ultimate computer science success blueprint quote that you should literally memorize for your exams. The USB-C allows 20V power connectivity, which means it can be used to charge much larger devices. By including this, you're showing the examiner you understand that USB-C isn't just a data cable, it's a 100-watt power delivery system capable of running full-sized hardware like laptops. Right, stop scrolling. Subscribe to our YouTube channel Ace the Exams at @acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 great boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Welcome back. Let's pivot to a harsh reality of physics. We have our incredible USB-C standard, but we live in a world filled with electrical interference. What happens if a 0 accidentally flips to a 1 during this high-speed journey?
Section 4. Catching transmission errors. This brings us to our interactive workshop, because catching errors isn't just nice to have, it's absolutely vital. Data gets corrupted, lost, or skewed constantly. Let's start Challenge 1, Data Scan. You have 60 seconds on the clock. Look at this complex parity block on screen. You need to extract the core trend. How does this actually catch an error? A parity check adds an extra bit to a data string to ensure the total number of 1 bits is either even or odd. Let's assume this system uses even parity. The receiving computer checks every single row and column. Look at row 8. It has 3 1 bits. That's an odd number, so there's an error. Now scan column 5. It also has an odd number of 1 bits. Did you spot the trend? The absolute genius of a parity block is that by tracing the intersection of the incorrect row and the incorrect column, the system mathematically isolates the exact single corrupted bit. It pinpoints the intersection, and the computer instantly knows which bit to flip back. If you can explain that intersection in your exam, you've nailed it. Moving to Challenge 2, Find the Flaw. I'm going to describe the ARQ, Automatic Repeat Request process. See if you can spot what students usually miss. Step 1. The receiver gets the data with an error detection code. Step 2. If an error is detected, a negative acknowledgement is sent back. Step 3. The sender uses a timeout feature. Step 4. The sender automatically retransmits until it gets a positive acknowledgement. So, what's the flaw in most student answers? They totally forget Step 3. For Challenge 3, your speed writing task, you must explicitly mention the timeout feature. If the sender doesn't hear back, positive or negative, within a specific time frame, it assumes the packet was completely lost and resends it automatically. Without mentioning the timeout, your explanation of ARQ is fundamentally incomplete in the eyes of a Cambridge examiner.
So, we can fix accidental physical errors. But let's raise the stakes for the final act. What if the interference isn't a physical accident? What if a bad actor intentionally intercepts the data on a public network?
Section 5, Securing Data with Encryption. This is where we bring everything together into our final system. We decode the command word, we apply the PL framework, and we manage our exam time perfectly. Encryption is the ultimate solution. It doesn't stop interception, but it stops comprehension. If you're asked to define encryption terms, keep it sharp and precise. Plain text is the original, readable data. Ciphertext is data that has been mathematically altered by an encryption algorithm into an entirely unreadable form. It looks like absolute gibberish to a hacker and is useless without the decryption key. Those are your baseline definitions to guarantee the first few marks.
But here is the grand finale. The heavyweight question compares symmetric and asymmetric encryption. Alex writes a novel. Sam writes a sentence. We write a boardroom strategy. Symmetric encryption uses a single shared key to both encrypt and decrypt the data. The critical vulnerability, your Peel explanation, is that sharing this single key over the internet is incredibly risky. If intercepted, the entire ciphertext is compromised. Asymmetric encryption is the superior solution. It uses mathematically linked key pairs, a public key and a private key. You share the public key freely so others can encrypt data to send to you. But, and this is the absolute kicker, that public key cannot decrypt the data. Only your private key, which never, ever leaves your secure machine, can unlock it. It completely eliminates the vulnerability of transmitting a secret key across the open web. Master this comparison and you are operating at the top of the grading curve.
We have completely demystified the data transmission journey today, from decoding the command words around data packets and routing, applying the Peel framework to directional transmission and USB-C hardware, to mastering the time management matrix for complex topics like parity blocks, ARQs, and asymmetric encryption. This is your cheat sheet recap, and your mark potential progress bar is officially sitting at 100%. Listen closely. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel Ace the Exams, at @AceTheExams_IGCS to excel in your Cambridge examinations. Subscribe right now to @AceTheExams_IGCS and click that bell. Don't let another exam pass you by. As computing power grows exponentially, how will these digital locks and keys evolve? That's the kind of high-level thinking that separates the good students from the great ones. Drop a comment below with your target grade for computer science and the biggest challenge you're facing right now. Our team responds to absolutely every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. See you in the next one.